Hi, it's Dr. Zach. Today we're going to use functional analysis to graph. So let's get started. Your lesson preview provided lots of clues as to what you should draw. I hope that the first thing you noticed is that you have an inflection point at 0, and then perhaps you noticed that you had asymptotes at negative pi over 2 and 3 pi over 2. Now, you're told that you have a critical number for when your first derivative was equal to 0, but it's not a relative min or a relative max. It's just a little bit flat. You're concave up and decreasing from your asymptote to that point. Then you are concave down and decreasing until you get to the next asymptote. For your lesson notes today, I want you to draw accurate graphs. And in order to draw these graphs, you're going to analyze all the different characteristics of f of x, f prime of x, and f double prime of x. From f of x, you should get your zeros and figure out your asymptotic behavior. F prime of x provides your critical numbers. Once again, that's where your derivative equals 0 or does not exist. You should determine where f of x is increasing or decreasing and determine the relative extrema. From f double prime of x, you figure out where f of x is concave up or concave down, as well as the points of inflection. Remember, you only have a point of inflection if your concavity changes. If your concavity does not change, it is not a point of inflection. When you put it all together, draw and analyze your asymptotes, plot and label your zeros, critical numbers, and inflection points. Draw your relative mins and maxes, write IP next to each inflection point, then connect your asymptotes and tail end behavior. Make certain that you are drawing your concavity correctly. All right, so for each of the next questions, you are to use the characteristics to graph. Let's get started with number 1. I'd like you to use the characteristics to graph f of x. Try to work these out on your own. Afterwards, check the video to see how well you're doing. So give this a try on your own and then check your answers. Now that you've done all the work, make certain that you're getting the same zeros and asymptotic behavior. Include the limit notation when describing your vertical asymptotes. For your critical numbers, it's sometimes easier to determine where the zeros are if you have found a common denominator. Make certain your statements are accurate. State where f of x is increasing. State where f of x is decreasing. State where f of x has a relative min or relative max. Give a reason. It has a relative min because f of x decreases and then increases at x equals 4. If you prefer to use f prime of x is positive and then negative, make certain that you state f prime of x when using positive and negative. When talking about concavity, once again, I made certain that I had a common denominator. Just a reminder, the sign chart is not graded. This is just for you. It is not going to be part of any graded assessment. The sign chart helps you evaluate what's going on. It's the statements, though, that are going to be graded. Sometimes it's good to build one sign chart to describe what's happening with all 3 functions, f prime of x, f double prime of x, and f of x. When you put it all together, draw the asymptotes first. Tell me where your inflection points would occur, wherever you're crossing your axis, and where you have a relative minimum. Use these sign charts to help figure out the graph, but the graph and its accuracy is what we're going to look for. Your next question is a bit more complex. So here we have g of x. Make certain that you follow through and find your zeros, asymptotic behavior, and then try to graph the function. Do your best to graph the function without looking at a graph first. So give this one a try. Afterwards, check your work. Perhaps you should factor g of x so that you can find your zeros a little bit more easily. Make certain that you discovered there was no vertical asymptote and no horizontal asymptote. The critical numbers became a little bit more interesting though. When you set your function equal to 0, you did have critical numbers at, you also had a third critical when x was equal to 1. This is where your derivative did not exist. So perhaps when you're thinking about whether you have a relative min or max, you should draw some sort of corner or point at 1 to remind yourself that it is not a smooth curve there. As you look at your second derivative, you notice that it never was equal to 0, and that the second derivative did not exist at 1. When you checked 1, though, you found that you did not have an inflection point. Your function was concave down everywhere on the interval, except at that 1, because your second derivative is less than 0. When you put it all together, you should have come up with an m. Make certain that you recognize that the point is sharp when x was 1, and that you have nice smooth curves when x is 0 and x is 2. Our third question deals with a trig function. H of x is equal to x cotangent x. Fortunately, we have a domain restriction. Now, when you're thinking about the zeros of this function, perhaps you should rewrite h of x to be equal to x times the cosine of x over sine of x. When you find the derivative and second derivative, let's go back to the cotangent function. Hopefully we'll be able to find the zeros of the first and second derivative. If not, don't worry, you will have enough information just by using h of x. So let's turn off the video, try the problem yourself, and then come back to take a look at your work. So first you found your zeros, and you determined that they occurred at negative and positive pi over 2, positive and negative 3 pi over 2, and that h of 0 did not even exist. Next, you examined your vertical asymptotes. Perhaps you thought that you had a vertical asymptote at negative pi, 0, and pi. But if you look closely, you actually do not have a vertical asymptote at 0. It is a removable discontinuity, or a hole at 0. So when you graph, you're going to have to build a hole at x equals 0. Next, you determined your critical numbers. Well, your derivative wasn't hard to find, but when you looked at the factored form of your derivative, it was really too tough to find any critical numbers. Next, you found your second derivative, which once again wasn't too tough to find. But as you were looking at your factors, did you notice that the inflection points were a little bit more challenging? What happens is we're actually going to have to use our vertical asymptotes to guide our graph. So go back to the information you found just related to h of x. Understand what's happening with your vertical asymptotes. The vertical asymptote was going downward near negative 2 pi, and it was going upwards near negative pi. Using the information from your sign chart, you were able to put in all the asymptotes, the holes, the zeros, and then you could get a really great looking graph with a lot of detail. So this is one of my favorite functions. J of x is x times the square root, 9 minus x squared. Let's find the intercepts of the function and the asymptotic behavior. Give this problem a try. Once you have worked out all the different characteristics of the function, graph it and check your answers. So one of the most important things you should have noticed is that the domain is going from -3 to 3. Now with that domain restriction, that tells you that you have no horizontal asymptotes, and also this problem has no vertical asymptotes. It does have 3 intercepts for us to consider, and that's going to help us graph the problem. Now when we describe and find our critical numbers, your critical numbers occurred once you found that lovely derivative. Yes, you took a little bit of effort there. Found the derivative and simplified. Your critical numbers occurred at negative square root of 9 over 2 and positive square root of 9 over 2. Then we determined that j of x was increasing on the interval between those two critical numbers, and it was decreasing on the intervals outside of your critical numbers. Once we found our critical numbers and our intervals for increasing and decreasing, we found the second derivative. And while the second derivative was complex, it's simplified so that you could find the factors. And you should always try to find the factors whenever you can. We drew a sign chart. Now, the sign chart is a guide to help you make the statements. And the statements we're looking for would be something like j of x is concave down on the interval because your second derivative is negative, and your j of x is concave up on an interval because your second derivative is positive. We also want to make a statement about the inflection points. So once we put all the pieces together, we have 5 points that you want to graph. We have no asymptotes this time, but that's okay. This graph is relatively simple, even though it started out quite complex. So one of my favorite graphs, I hope you enjoyed that. And now you're going to do a little bit of practice. If you take a look, you have 5 questions to practice. These do take a bit of time, so follow those steps and do an awesome job. You have a great day.